What's up, guys? Welcome back to another LeetCode, and today we're going to try and solve LeetCode 46 permutations. So, pretty simple question to understand. Just given an array nums of distinct integers, return all the possible permutations. Cool. So let's dive right in. So immediately, I know this is a backtracking problem because it sounds like it, and that's also where I clicked on it from the LeetCode roadmap, but that's a problem to solve for another day. You can do this with the Python library. I think it's called itertools. I don't think so, or maybe. But same with the subsets. You can just use there's built-in libraries, but that's like just calling the sort on a sorting question. So let's try and do this on our own. So I think approaching this, we need to be able to make a set of smart decisions at every number. So we know that it's not like subsets where some of these are smaller. They're all going to be the same length as the input list. They're just going to be in kind of different orders. So let's see how we can approach this. So we got our 1, 2, 3, and we start out with an empty list, which is our, candidate perm or whatever. And I think we may need to, we start here, we need to make a choice of whether we add that or we don't add it. So we can add that on that branch and not add it on this branch. And then we would kind of move to the next number, and here we can choose to add it. And we can choose to not add it. I'll just deal with this later. And then we go here and we would choose to add it or not add it. And then we would bowl back up and we'd be here. And we would still be at the 3, because this is, if we had some sort of index per depth, it would be 0, I guess this would be wrong because the first one is just kind of our root. We haven't even done anything yet. 0, 1, 2. So we can do 1, 3 here. We can not add anything here. But I guess you guys kind of see the issue. We get down here and we're just kind of doing subsets and not permutations, So I think the first case where this becomes interesting is this one right here. Because we've traversed down our tree and we've decided to skip 3 on this instance. And we're at 3, our index is this. Or I guess no, this isn't the interesting case, because this one would just die. We just kind of don't need this. It's this case where we have the 1 and the 3, because we need to somehow be able to know that we want to then add the 2 after, which is what I'm struggling with mentally. So we can either add the current number or we can not add the current number. And we would go to the next one. We can either add it or not add it. And then we go to the next one, we can either add it or not add it. But that leaves us with a lot of unused branches. This isn't used, this one won't be used. Any leaf node where we take the not add transition would end up in an ordering that we don't use. And initially I was thinking, or not initially, but now I'm thinking we can run this, and if our leaf node is not the length of the nums, we can just run it again. And I'll try and code this because maybe this is just the solution, and maybe the optimization will jump out to me once I have some code. But I'm just going to basically try and compute the subsets, but for the subsets like this one and this one, where the length of that leaf node is not the same as the length of nums, I'm just going to like restart. And then hopefully just catch the one that I missed. Like only add the ones that I missed. So that picture might not have made that much sense, but this is enough for me to continue here. So I'll hold all the permutation, and I'll hold the current permutation, and I'll have my DFS, which I'll call, and then I'll return the main permutations. And inside here we need some base cases. So if I is equal to length nums, just for starters, definitely return. Well, I guess if it's equal to, then we would actually like to add it. And if it's not equal to, or no, not if it's not equal to, but if it's greater than, then we would like to just return from this branch, because we've gone too far. And then we would like to call this on either doing something or not doing something. So this is my not don't do anything case, and this is my do something case. So on this case, we would like to append nums I, and then pop that off. And this will generate us our subsets. Well, actually, only the subsets where the length is equal to nums. So I'm either adding it or I'm skipping. But maybe it's different because I'm going to run this and see what output I get. I think it's going to be all the subsets of length 3, which is just one subset. No, it's all of them. I guess it's because of the I. So I do get all the subsets pretty nicely, and that's something I couldn't do this quickly before, so that's good. Good to know. But our positive base case needs to change. It needs to be when the length of that permutation is actually the length of nums. But maybe this can be useful for me. I'm going to leave that there for now. So yeah, this is just giving me, but you see, like, okay, this is a useless branch, but this one, if I just were to append the 2, then it would work. And this one, if I were to append the missing 1, that would also work. And these two, I need to append the 3 and the 1, or the 1 and the 2. So are they saying 1, 2, 3, 4, 5, 6, 7, 8? 1, 2, 3, 4, 5, 6. There's not the same number of them. So not all the branches are actually useful. I think I'm making the wrong decision. I need to add. Right now I'm either adding the first number or not adding the first number, but I think that's the wrong decision. What if I were to add, add the first number, or add the second number, or add the third number? I don't know, that wouldn't work. if I did something, so this is when I'll actually return. And what if I just kept going until I got that? I mean, this might mess it up, the second base case. But, I see. Well, actually, this doesn't make sense, because yeah, now this one only gives me this means I'm out of bounds. So I do need to return if I'm out of bounds. But like, do I reset? Would that reset me? No, that can't be true, because I think I'm going to go back up. If I only return once, I only return up one. How about that? If I update the index? So I'm starting here. And maybe I need to do this starting at each of these three. Or 1, 2, 3. That also wouldn't do it. I know this is good, adding the first number. What if I add the second number, and then add the third number? But how would I, like, actually keep track of this? Because then I've already added the first number, so then I'd add the second number to it. I kind of like this more, actually. But then the tree would be different. It would start with 3. And then it would, like, blow up, or, you know, there'd only be one thing to do after this. You guys get the idea. But how would I actually translate this to code? I'd like the structure I've been able to do up to this point of just like having the recursive calls in here, but what this entails for me is that I can't do that anymore. I don't know, but do I need like a new index or the same index? So this would be that, and then I would try that. Well, I'd have to actually try it, so I would do that. And then I would pop, but do I need I now? I would like to start somewhere. But every time I go down, maybe I do need it. Because if I is, let's say it enters in as 0, but I think it would be something like this. 0, 1, 2. But then j would be like 1, 2, 3. So I enter in as 0. I guess what would my base case be if I is length nums, return 1. I like this. And if the length is, I guess these are still good base cases. But also, I don't know if I send j, well, maybe I want to send I plus 1 still, but I want to append j. Ooh, what's this gonna give me? Whoa, holy shit, am I the GOAT? Did I just figure this out? I like it a lot, because now I had foreseen this problem, although I didn't talk about it. I'm looping through all 3 every time. I want to only loop through the ones I haven't seen. So, at a minimum, it's going to be length of name nums minus length of the current permutation. But if nums j in perm, whoa, maybe I don't want this. So if the number is already in the permutation, don't do it. Wow. Or maybe this will work. Oh my god. Am I figuring this shit out? No way. I did not think I was gonna get this. Let's go. Oh my goodness. Straight intuition. I didn't look at anything. I swear to God, I've never seen this problem. Sometimes I glance at the solution before just to just so I'm not like sprawling around wildly. But recently, so I haven't been uploading because I'm trying these raw. I'm going in, no protection. And it hasn't been working for me recently. I'll get too off course and the video will get too long, so I won't upload it. But whoa, I like this. I mean, our runtime stuff is pretty bad, actually. But I believe our complexity is correct. This is correct. It's factorial for, well, it's the first time I've written a factorial complexity code. I don't think I've ever done this before. Why would this be factorials? Because I have O of... Yeah, because this is not... Dude, it is factorial. Because I have 3, 2, 1. And this is why... this check is why I'm n O of n times n factorial. I guess I wonder if I can get this check down to constant and whether that would be better. But I don't think that's worth my time. I think it's a good solution. I'll end it here. Alright. Thank you guys, and I'll see you next time.